Now it's time to build the first ever neural network. So as I said, we're using Keras. As you see here, what we do is very, very simple actually. We're just creating a model and we are adding layers to it. So basically model add a Keras layer, model add a Keras layer, model add a Keras layer. So it's quite simple. In theory, but of course you can go as deep as you want. So let's start with the first line. We have model equals to Keras model sequential. There are three ways how you can create models with Keras. So you have the sequential class, which is very simple. You just choose the predefined layers and then put layers on top of each other. There is a functional class, which is a little bit more detailed. You can create more complex neural networks with that one. But we don't need the functionality now, so we're just using the simplest one. There is also a models library inside Keras. And for that one, you basically make everything from scratch manually. And that is more for if you're doing research and if you're trying to achieve the highest possible accuracy. And that's not really something that we need here. All right, the second line here is a layer that we're adding, and the first layer that we're adding is basically the input layer. What is done here in the flattened layer is, because we have a 28 to 28 matrix, we want to make it one big string of 784 pixels. That is 28 times 28, 784. And I am saying the input shape is this much, please flatten it. And flattening it means that adding them one after another, making it one long line. And that is the number of inputs that we're going to have. The next line, we are creating, actually the next two lines, we are creating hidden layers. Hidden layers are called dense layers here. Well, not specifically hidden layers, but all the layers are called dense layers. That means they are connected with everything that is before them or after them in a dense way. So you might hear this word in other places too. You have dense and sparse. Dense means every neuron is connected to every other neuron. Sparse means not every neuron is connected to every other neuron. So there are some missing links in between. And sometimes you need that too, but we will talk about that in the future lessons. So right now all we need is dense layers. For the first hidden layer, I have a 300 neuron layer, and I'm going to keep the activation value because, as we talked about, as we mentioned briefly in the previous lessons about the building blocks of neural networks, value is one of the best ones that we can use, especially for hidden layers. Same for the second hidden layer. We have 100 neurons, and we are setting the activation to be value. And the last one is our output layer, actually. We have 10 output layers. And why is that? It's because there are 10 classes and we want to classify our images, the input images, into 10 different classes. So that starts from 0 to 1, 2, 3, all the way to 9. And that makes 10 different classes. And we want our model to make a prediction for each of these classes. So every time we give it an image, it's going to tell us how likely it is that it's a 0, and then how likely it is that it's a 1, and so on and so forth, and also how likely it is that it's a 9. And at the end, we will have the possibilities of which number this image is. Here, you might realize that we're using softmax. Softmax, I'll just quickly show you what it looks like. So it looks like this. It goes from 0 to 1, and in that case, it looks very similar to sigmoid. But then you can ask, why are we using softmax and not sigmoid? Because in this exercise, in this problem specifically, the classes are not related to each other. So they cannot, one image cannot be half one and half the other. They are completely independent, yes. And what sigmoid does is it creates possibilities, it creates probabilities that are independent from each other. The same thing can have 0.5 possibility to be two different things. Whereas for softmax, all the possibilities, the summation of all the possibilities lead to 1, so they sum to 1. So that means that if possibility of an image being 2 is higher, that means possibility of it being 3 needs to be lower. And that's the kind of thing we need, because the images we give can only be one thing, they cannot be multiple things. And that's why we're using softmax. So once we build our model, we can look at a summary of our model. So this is a nice little function that tells you what your model looks like. Let's see. So as I said, the flattened layer, the input layer, has 784 neurons. The dense layer has 300 neurons. The first hidden layer, the dense two, they cannot be called the same thing, so that's why they have the _1 and _2. The first hidden layer, it has 300 neurons, the second hidden layer has 100 neurons, and the output layer has 10 neurons. And for each of these, we also have the number of parameters, and also we have a total number of parameters. And what are these parameters? As I said, for every connection between two neurons, we have the weights, and for every neuron itself, we have the bias. So in total, we have a lot of parameters. And what our model is going to do is update this weights and biases to give us the best accuracy possible. And if you want to do it, you can also take a look at what your layers look like. So Keras basically has a lot of nice functions or commands for you to look into the model that you build. Of course, it's not always going to be this simple. You're going to build something more complex sometimes, and you might need to look at some summaries or look into the layers and see what you built. The next thing that we want to do is to compile this model. So it's here. What we're doing is we're basically giving it some hyperparameters here. And hyperparameters are things that you have to set yourself beforehand. They cannot be learned. So parameters, as you see here, are things that are going to be learned. It also says trainable parameters. These are all going to be learned. So they're going to either be initialized to 0, that's for biases, or they're going to be initialized randomly, that's for weights. But on top of that, while you're compiling your model, you also give it some hyperparameters. So these are things that you basically hard code and that are not going to be changed. All of these options, you can actually see for all of these things what options that you have. So for example, for loss, we're using sparse categorical cross entropy. And that means that is this thing, sparse categorical cross entropy, is how we're going to measure how good our model is doing. So you have some other ones too. So let's go here. I'll show you some other options. So for everything basically on Keras, you can see what options you have. So it says probabilistic losses, regression losses. After a while of working with deep learning or generally machine learning, you'll probably have an idea which one to use. But generally, if you don't have an idea, you can Google for it, or you can come and look here at the options. So let's go and find the one that I'm using right now. Sparse categorical cross entropy. And it says use this cross entropy loss function when there are 2 or more label classes. And that's what I have. I have more than 2 label classes right now, and that's why I'm using sparse categorical cross entropy. But as I said, based on your problem, if it's a classification regression problem, or what do you want to get out of it, and the type of output that you're getting, you're going to want to change this, of course. But yeah, we will talk more about these in the future also. Optimizer, we are using a stochastic gradient descent. Again, you can find the available optimizers here. Let's take a look quickly. So we have this one, the gradient descent one, ADAM, AdaGrad, AdaMax, NADAM, all of these things. Of course, these are not only made randomly, these choices. So right now we are using gradient descent because that's kind of like the basis one that you use. But if you want to make your model faster, for example, you can use some other things. But as I said, we will go take a more systematic look on which one to choose and when in the coming lessons. The last one is the metrics. This is basically what you want your model to report on while it's training. So you don't only want to see the loss reported. If you want to see some other things reported, you can also add them here, and then your model will report it for you. So let's compile this model. And I don't need this one right now. Yes. So the last thing that we are going to do is basically fit the model around our data. And that's why here we have the training, X and Y values for the training. And we have some other things I'm going to explain. The one thing that you might want to know, again, here is a website where you can see what are the options of things that you want to set. So here you're seeing I added the data set, the X and Y value for the data set, what the model is going to fit on. But on top of that, I am setting the epochs, validation data, and batch size. And these are not the only things you can set, of course. You can set all of these things. So right now I'm giving X and Y, I'm giving batch size, I'm giving epochs, I'm also giving validation data. And these are all the other things that you can still set. We don't need to do them right now, but you can come here and read what they all mean. So for example, verbose would mean give me more information about what's happening while the model is training. Or for example, instead of giving the validation data here specifically, we can say validation split and say like this, validation split equals to 0.1, so that the model will set aside 0.1 of the whole training set aside to use as validation data, so you don't have to do the split beforehand. So these are all the options that you can, of things that you need. You don't need to use them right now, but just in the future if you want to check it out. And also these values that you see here as equal are the default values. So if you don't specify it, this is what it's going to be like. So if you don't specify the epoch, it's just going to be 1. All right. So here what we do, as I said, we give the training input and the training true values for the output. Epoch means how many times I want this model to be run on the whole data set. And batch size means how many data points are going to be given to the model at each time. And these things are kind of hard to compare. That's why I also written a note here. You have access to the notebook, so while you're working on it, you can also read these little notes and use these little links. But so here's how they're different. Batch size means every time the model is running, so if you remember backpropagation, what happens is we calculate all the values, and backpropagation looks at the loss and then changes the weights and the biases of the model. What happens here is, if you do not have a batch size that is smaller than the number of instances that you already have, what's going to happen is the model is going to be trained on all data points, and then it's going to be updated. But that's kind of slow at times. That's why we sometimes use mini batches, and mini batches can be as small as 13, 16 even. What you do is you train the model on only 32, as stated here, 32 examples, update all the weights and biases, and then you take the next 33 and do the same thing, and the next 33 and do the same thing. And once you're done with all the training examples, you have done 1 epoch. And you do this 30 times in this training, and that means you've done 30 epochs, but you trained it on a lot of different batches. So once we run the model, maybe it will make more sense for you. Let's see. So as you see here, we have the epoch number. It says 1 out of 30. This was the first epoch, the first time the model saw all the examples. Here we see how fast it's going. We see how the loss is changing for the training, how the accuracy is changing here. And after it's done, it also calculates these things for the validation set. So we've already given it a validation, right? So as you see here, the validation loss is getting lower and lower. And validation accuracy will be here. It's also getting higher and higher. And basically, this training loss and accuracy, these are the training loss and accuracy. I guess I can only select these ones, but anyways, these two are the training loss and accuracy, and we have validation loss and accuracy. And if you see that your model's loss, training loss, is getting lower and lower, whereas the validation loss starts getting higher at some point, that means your model is starting to overfit to your training data, and we don't want that. So this is one way of looking at it. What else? So we have some other numbers here. This is the amount of batches that we have. So we said we have 32, we want to put 32 examples inside the model every time to train it and to do the backpropagation and the gradient descent step. And that means that our model runs on 1,719 steps. So it's basically, let's remember how many training examples that we had. Of course, this needs to finish first. It's nearly done, so let's wait for it. All right, so it's done. I just want the shape So we have 55,000 examples. And if I divide them into 32 chunks, what we have is 1,719. Well, you have to round it up, different groups. So it's like 32, 32, 32, 32, 1,719 of them. And when it does all of these passes, then we have done a whole pass on a whole data set, and then in the whole data set, and then it goes to the next epoch. So let's look at some things here. The loss, as we see the training loss, I see that it keeps getting lower and lower and lower. It's a good thing. It means that we are fitting the data set very nicely. The accuracy is also getting higher and higher. Let's look at the validation loss. It gets lower here. Nice that it gets lower and lower. Well, now that I see that it gets lower and lower, maybe I could have increased the number of epochs even. Maybe I could have trained this data set, this network for longer. And I also want to look at the validation accuracy. It also looks like it's getting higher. So that's perfect. As you see here, sometimes it got a bit lower. So it was, oh no, it didn't. Yeah, I guess here it did. It was 0.98 and then it went back to 0.9794. So I guess after a while, our accuracy didn't really increase much anymore. So it's good to know that there is a limit to how much we can train this data set. So the best size for the batch sizes is, I've read somewhere that it's actually best if you set it to something like the increments of 2. So it's, 16, 32, 64, 128, 256 sort of thing. It's because basically how computers are built, and this network, while training, of course, is using the processor of your computer, and that is based on the bit size system, right? And that's always in increments of 2. So they say it makes it faster to use increments of 2. So I can, of course, change the batch size to something else if I want to, and if I can run it again, but it's going to run a little bit slower. That's because now the model is calculating the partial derivatives that we talked about and doing backpropagation and gradient descent every 10 examples. And that's going to make it a little bit slower because of all the calculation that needs to be done. And as you can see, now we have more steps to go through. So we have 5,500 groups of 10 examples together before we can calculate the partial derivatives and do gradient descent.